So let's talk about the Huygens principle of the wave theory of light. And there is a video link here you can watch for more detail. Okay, so let's talk about this theory. So in this case, we are talking about light is a wave. Now, light is a wave. Okay, this means, for example, if we have like this source of light, then it will emit light everywhere. So these are the rays, you know, if we are considering the geometric optics, these are the rays. Okay, rays. So rays basically gives the direction of propagation of wave. Okay, now it will be traveling everywhere. So this is the source. This means at particular time all light energy will be in this kind of circle. Another time it will be here. Okay, so these are called the wave front at time t1, and this locus, this is called the wave front at time t2. So from here it is clear that wave front is perpendicular to the rays. Okay, so if we define the wavefront, in general we say that it is the locus. Wavefront is the locus of all points in a wave at a given instant, at a given time. Okay, so for example, if you consider only this time, so this distance will be same. For example, this is the air, then it will be c times t1. This also distance will be c times t1. So every distance will be c times t1. If you consider the other part, say we are here, if you consider this will be c times t2. So it is the locus of the all points. Okay, so in this case the wave front is not a plane. This is called the spherical wave front. So this is the spherical wave front. Okay, so similarly we can talk about the other kind of plane wave front. Say for example, we have this kind of beam. You know that this is a parallel beam. So light is coming from very far away. So these are the parallel rays, parallel beam or rays, whatever we call it. So you know that if we draw perpendicular line, these are called the wave fronts. So these are the wave fronts. So wave front and rays are perpendicular to each other. So this means this will tell you this is the locus, this is the wave front at time t1, and this similarly, this is the wave front at time t2. Okay, so the light will be traveling in this way. So in this case, though these alls are parallel, so we can say this as a parallel wave front. So we call at this as a wave front, but this is a plane wave front. This is a plane wave front. Okay, so let's move further. So let's move forward. We're saying that our main question will be how to get wavefront at time t2 if we know wavefront at time t1. Okay, this is our main question. Means basically how to know this location, second location, if you know the initial location. So that's how we are using the principle of the Huygens principle. So what it says, Huygens principle says that every point on a wavefront is a source of wavelets that is spread out in the forward direction at the same speed as the wave itself. The new wavefront is a tangent to all the wavefronts. So let's see what does it mean. Okay, let's start that. Say we have say we have this wavefront. This is the wavefront at time t, okay, in air. Say for example we are talking about in air. Okay, so what will happen according to law, according to Huygens principle, every point, there are infinite points, every point on the wavefront behaves as a source. Okay, so this every point, so in this case every point on the wavefront behaves as a source. Okay, this means after certain time, say this source is spread out forward, say it will be here, say so we are talking about at time t1, so it makes a spherical outlets of CT1. This also behaves as a source, so it again makes the spherical outlets. So each source will be like this. Okay, so each source center as this. So what I'm saying that if this is the source, it will spread light everywhere. So this distance will be CT1. So in this case, we are just taking the first half. We are taking this first half. Okay, so this distance will be CT1, CT1. Okay, so we are taking basically this first half. Okay, forward. According to law, we have to consider the forward. So because you know that light will not go backward. So in this scenario, we are getting like this. So if we draw a common tangent, this is the common tangent. This will gives the new position of wavefront after time t1. Okay, so the basic concept here I will tell is this: if this is the source of light, these are the wavefront at different time. Okay, so if you draw rays, they are parallel, they are perpendicular to the wavefront. Okay, so we are taking the forward. So in this scenario, we are taking this side because light will not move backward. So these are the wavefront. Okay, so if you consider the parallel wavefront, we get the similar thing. So we can say that based on that, we can explain the phenomenon of reflection phenomenon of refraction. In this case, this can be explained by wave theory of light. Okay, what does it mean? That we can show that sine I over sine R equals C over V. Means if light is traveling from, say, I have this medium is air, other medium is glass, this angle of incidence is I, this angle of refraction is R, then we can show that sine I over sine R is equal to the speed of light in air over the speed of light in the glass. Okay, this is for the refraction. In the reflection, we can show that I equals R, and angle of incidence, angle of reflection, and incident ray, refracted ray, and normal all lie in the same plane. Okay, let's talk about that. Okay, so this is a video link. They talk about both the reflection and refraction. Now I'm going to show how we can use this theory, is called the wave theory, to find the laws of reflection. Okay, so let's start with the drawing. Say I have this medium. Okay, this is the medium, separate, this is the interface. So I have, this is the medium 1. Say I have this has refractive index eta 1. I have other medium 2, it has refractive index, say, eta 2. Okay, so you know that at any time we can consider a wavefront. So this is, say, this point is A, this point is B. So in this picture, AB is the incident plane wavefront. If you take plane wavefront, it is comparatively easier to do the math. So you know that any outward drawn perpendicular behaves as a ray. So if you draw the perpendicular to this AB, this will represent the rays. Okay, so for example, if I am going to draw perpendicular line like this, okay, these all will be the incident rays. These are the incident rays. Okay, so let's move further. That say according to the principle, Huygens principle, A and B behave as source for secondary wavefront. Okay, you can also call it secondary wavefront. So we can say in time t, okay, in this time when secondary wavefront or the wavelets reach from B to B prime, means, say, now this will be reaching at this point. Okay, so it is reaching at this point. I would say this as a B prime. In the same time, wavefront wavelets reach from A to say A prime. Say means it may be somewhere. If this is the source, it will spread out light. If this is the source, it will spread the light. Say we can draw like this. Okay, so maybe if I draw perpendicular like this, it will be here. It will be the point A prime. So you clearly see that BB prime and A prime are not equal, because BB prime, you see here in air, and you see A prime, say glass, in different media. So light will travel different distance in different media, so they are not equal. Okay, so you know that if we draw a common tangent at that time, so these are the distance travel in same time. These are the distances covered in same time t. In time t, the wavefront will come from B to B prime, and at the same time, the wavefront that start from A will reach to A prime. Okay, but they are in the different media. Okay, so let's draw the perpendicular line over here. So you know, I can consider this angle is θ1. Okay, from geometry, you can see this angle is perpendicular 90 degree. So this angle is also θ1. Okay, similarly, the outward drawn perpendicular, these are the lines perpendicular to BB prime, these are the reflected rays. Okay, so this will represent refracted rays. Refracted rays. Okay, so we have to consider the angle. If this angle is θ2, then again, by using the same concept, we can say that this angle is also θ2. Okay, so let's do some math over here. Sine θ1. Let's do sine θ1 is equals to BB prime over AB prime. Okay, BB prime over A prime. Let's see. Sine θ1 is BB prime by AB prime. Okay, and sine θ2 will be equals to AA prime over AB prime. Okay, then light is traveling from A to B, so we can say n eta21 is equal to sine θ1 over sine θ2. So this will gives you refractive index of medium 2 with respect to medium 1. Okay, so I will write this as eta 1, I further simplify, air times refractive index air over 2 sine θ1 over sine θ2. Okay, then I will write as eta2 air. If we flip that, this will be eta1 air. Okay, so sine θ1 over sine θ2. Then I can rearrange eta1 refractive index of first medium with respect to air times sine θ1 equals equals refractive index of second medium with respect to air sine theta 2. Okay, in general we don't write air, so eta 1 sine theta 1 equals eta 2 sine theta 2. So this is the same, this is the Snell's law we talked before. So this means eta times sine theta equals constant. Okay, so we got the Snell's law. So this is the Snell's law. Okay. We can further simplify this as eta 1 sine theta 1 is b prime over ab prime. Okay. Eta 2 is eta 2 times sine theta 2, which is a prime over ab prime. Okay, so we can cancel this and that, but we know a prime, this will be in the medium, so we can write it is p times t, and b prime will be equals to c times t, because you see here that p is the speed of light. Speed of light, we are taking particular color, say it may be yellow. Speed of light in medium 2. So say for example it is glass or water. C is the speed of light in medium 1. In this case, say this is air or vacuum. Okay, so you know that C is roughly in air or vacuum is 3 times 10 power 8 meters per second. Okay, now we can plug those values. So eta 1 bb prime is equal to C times t, eta 2 equals a prime, which is p times t. We can rearrange, so it gives you eta 2 times c equals eta 2 only p. Okay, so in our case, say eta 1 is 1 for air, and we are supposing n2 is just n, say for example for say glass. Okay, if we plug these numbers, what will happen? C equals eta times p, then eta equals c over p. Okay, this is the another definition of refractive index. So refractive index can also be defined as the speed of light in air over speed of light in, say, in this case glass. So that's how we also defined at the very beginning of the chapter, maybe. So we can say like this. Okay, so if you understand this part, we can show the laws of reflection. Means we can show that I equals R. Okay, so I recommend to watch this video. It has steps. Okay, in this video link, if you go over, they will show you step by step how to prove I equals R. Okay, similarly, just like in the refraction we did, reflection will be done in the same way. So You have to derive laws of reflection using wave theory applied. Okay, so please show all the steps. These are the further resources. If you want to watch more, some are from the Khan Academy, some are from the other resources. Okay, some are the great resources. And one great resources here is all the simulations that I showed you from this site. So there are a lot of useful simulation over there. Okay.